Professor Hadas?
Hi, yes.
Yeah, hi. You could able to now share the screen or present?
Yes.
I
Now
have
it's
made
fine.
you as a host.
Yes, thank you. It's fine now. Thank you.
Fine.
Okay.
Hello, Professor Adas.
Yes.
This is Padmanabhan.
Hi, hello.
Hi, how are you?
I'm good, thank you. I'm very good.
It's fine, ma'am. How things are going there?
It's okay. I think it's like everywhere in the world. I think it's about the same.
Okay, fine.
But I think we're kind of used to it, so I don't know. I'm
Yeah.
just
Okay. That's nice. And as we discussed earlier, we have started working on a toxicological perspective.
Mm-hmm.
Yeah, in that during our earlier discussion during ICWR, we have initiated some work on toxicological. So that I will update you shortly. Okay. So soon after finishing this meeting, I will send you a mail regarding that.
Oh, wonderful! Thank you.
Yeah. So based on the degraded metabolites, we have based on the earlier discussion, the degraded metabolites and its toxicological effects, we have started working. So that I will send it to you soon.
Yes. So I'm looking forward.
Yeah, sure.
Thank you so much. Thank you.
Professor Hadas?
Yes.
Yeah, we can wait for 5 more minutes.
Yes, sure, no problem.
Yeah, okay. Professor Hadas, can we start?
Yes, we can start, sure.
Yeah. So good afternoon all.
Thank you.
Today we have the second lecture on this course that will be dealt by Professor Hadas. She would be taking us around the properties of nanomaterials in continuation with the first lecture, right? So I think Professor Hadas, you can now take over, and this lecture will be for an hour, and then after this, Dr. Ram will be taking the next lecture.
Okay, hello everyone. So it's a pleasure to be here, and as Dr. Banidaran said, I'll be continuing a discussion about properties of nanoparticles. And since you've done such a wonderful job, then I will continue on also to see if I can get advanced with other topics. Just to tell you a little bit about myself, I'm a professor at the Tel Aviv University. My background is chemical engineering, and my passion is to develop sustainable technologies for purifying water and wastewater reuse. With that regard, nanomaterials and the nanoparticles have a huge influence on the development of technologies to solve and combat different issues related to water quality. Therefore, environmental engineering is I would say, is a very interesting field because we are able to combine many disciplines in order to solve the challenges that we have in the environment today, which span from climate change to water scarcity and so on. So I will start with the lecture, and it's a real pleasure to be here. Okay, so we can start. So the content of the lecture, and I will touch upon a few of these topics, relate to the types of nanomaterials and their dimension. They have also very special features. There are many factors that control the physical properties. There's issues that are related to the size and the shape of these nanomaterials. In addition to that, there are various different properties that are actually impact one another. So for example, the size and the color, the size variations, the size versus the melting point, size versus the surface area or the surface energy. So all these properties are very important when we try to understand how to integrate nano materials and nanotechnologies into application. This course will be mostly discuss the application of nanomaterials in order to combat and solve different challenges that relate to water and wastewater. So as already discussed in, there are many definitions to nanotechnology, and the National Nanotechnology Initiative, which is the NNI in the United States, actually define nanotechnology as the understanding or the control of matter at dimensions between 1 and 100 nanometers, okay? And this unique properties actually allow for novel applications. And since we discussed the types of nanomaterials and their dimensions, I'll just go over quickly and just remind you that 0 dimensions actually relate to the nanoscale, where none of the dimensions are larger than 100 nanometers, okay? So it can include, for example, nanospheres and nanoclusters. 1D means that we have actually 1 dimension outside of the nanometric range, okay? And again, 2D means that we have, for example, 2 dimensions out of the nanoscale range. And this can relate to nanoplates and nanosheets, and 3D, for example, can relate to nanoballs and nanoflowers. Now, the factors that control the physical properties of nanomaterials relate to the size, the shape, okay, whether it's spheres, rods, platelets, for example, composition, the crystal structure, surface ligands or capping agents, and the medium which the nanoparticles are dispersed. So if we look at, for example, the crystal structure, FFC means face-centered cubic, and BCC means body-centered cubic. And if we look at the cubes here, we can see a simple cube, okay? And then we can look at this image and we can see a body-centered cubic unit. And then we can look at this picture and we see a face-centered cubic unit, okay? So we have here different crystal structures. Then the surface ligands or the capping agents are also very important as they act as a stabilizing agent, and they provide the colloidal stability, which is of course very important with nanotechnology because we want to prevent agglomeration and coagulation of the particles. And we want to also stop an uncontrolled growth. Therefore, the capping agents are really important. And they are actually absorbed to the surface of the nanocrystal, okay? Thus, the capping agents are a key to attain to attain avoiding agglomeration and the stability of the nanoparticles. If we look at this image, we can see, for example, the bulk versus the nanoparticles. And there's a high percentage of surface atoms in nanomaterials compared to the bulk materials, okay? And the different properties between the bulk, and we can see here the nanomaterials relate to the shape, the optical, the electronic, the magnetic, and the mechanical. And there are different properties that we need to consider, such as the melting point, the reactivity, the mechanical, electronic, and electrical properties, as well as the magnetic. So all these actually differentiate between the bulk and the nanoparticles. Okay, so it's really important to understand that, for example. So how does the size impact nanoparticles? First, we need to understand that when we look at the number of atoms, this relates to the molecules between 1 to 10 atoms. And if we have between 10 to the third to 10 to the fourth, that relates to the nanoparticles. And then the bulk relates to more than 10 to the sixth number of atoms. And this actually has a huge impact on the properties of nanoparticles. So when we look here at, just see this image, we can see that within the bulk, the material properties of gold and silver do not change, are not impacted by the size. But when we go to the nano particulate range, we can see that the properties actually are really impacted by size. And we can look at this like beautiful image where we see silver spheres at the size of 40 nanometers, 80, 120. And we can see how the different sizes impact the properties and the color of the nanoparticles within the solution, okay, that are dispersed within the solution. So the size does have an impact on the color, for example. And another property that also was discussed before is the size versus the surface area, okay? So this is, of course, obvious, I would say, that there's an impact of the size on the surface area. When we look at, for example, at this table, please have a look, for example. We have here the nanoparticle diameter, okay, in nanometer and then in micron, volume, surface area, and the most important property is the surface area versus the volume. And what we can see here, okay, and this is like pretty obvious, is that when we decrease the diameter, we have increase in the surface area per volume ratio, okay? And this parameter is very important for us because the size affects the size of the bulk crystal. When it's transformed to a nanoparticle, it actually has, as we said before, it actually impacts the various properties, okay? And because of this unique property, nanoparticles are actually very successful in a wide, I would say a wide variety of applications. So this phenomena is very important. So for example, if we look at catalysis, the large surface area to volume results in, for example, it can result in high density of the low coordinated atoms and of the surface properties, and they render those properties more reactive. So this also impacts on the reactivity of the catalyst, and the reaction energy can also relate to the catalytic activity or the photocatalytic activity. We'll discuss this a little bit about this also later. And also it can impact the structure. So these phenomena of the particle diameter versus the surface area to volume ratio is very important. Now, another important point is the size versus the melting point, okay? So melting point of a substance, what does it mean? Melting point actually means, is actually the temperature in which it changes the state from solid to liquid, okay? So it's the temperature where the particle would the substance will change its state from solid to liquid. At the melting point, the solid and the liquid actually exist in equilibrium, right? So they exist in an equilibrium, and the melting point depends on the pressure. Usually the melting point is specified at a standard pressure. So let's look at this image, for example, or this one. We can see that the y-axis here is melting point and the x-axis is particle radius. So what do we see? We see that when we decrease the particle radius, the melting point also decreases. So what does that mean with respect to gold nanoparticles? It means that when we reduce the size of the nanomaterial, okay, we also reduce its melting point. Now, when we look at the equation of the melting point of the bulk minus the melting point, the temperature for the bulk melting point minus the temperature for the nano melting point, it is actually related to the surface energy divided by the diameter. So therefore, increasing the diameter has an impact on the nano melting point. Okay, so this is very important. We can also look at this graph here, and we can see on the y-axis, again, the melting point. And on the x-axis, now it's not the particle diameter, so it's very important when we look at graphs to look at the x and y. So it's the inverse particle diameter, okay? And again, we can see that with the smaller particles, we have a lower melting temperature, okay? Which is independent on the size, for example, in this case. So these phenomena are very important. When we think of thermodynamics, okay, so of small particles, the surface energy is an essential parameter. And in many cases, it's a very dominant quantity. Okay, so the surface energy is a dominant quantity. However, it's really puzzling that there's uncertainty with this parameter. Okay, so there's a lot of uncertainty with the surface energy. Generally, as I showed before with classic thermodynamics, we have a decreasing value of surface energy with decreasing particle size. Okay, so if we look at here, we have a decreasing value of surface energy with decreasing of the particle size. So this is a very important phenomenon. And why is this happening? This is happening because we have a reduced number of neighbors. Okay, we have a reduced number of neighbors of surface atoms when we decrease the particle size. Okay, and this results in the decrease in surface energy. And this also has an impact on the decrease in the melting point and the temperature of the melting point. Okay, so all these phenomena are actually related. It also relates to the surface tension, as you know, by the Gibbs theory. And therefore, the analysis of the surface energy data of nanoparticles and the dependence of the surface energy on the particle size and temperature are very important features, because that actually impacts the phase of the nanoparticle, which is also impacted by the size. So just to make a summary of these things, when we go down to the nanoparticle phase, there is an impact, various types of impacts. So it can impact the surface energy, the melting point, and also other parameters. Now, when we think about reactivity, okay, the electronic structure of nanomaterials depend on their size. And we saw that decreased size enhances the surface area, right? If we go back to this area, we see here that decreased size results in an impact on the surface area versus volume ratio, okay? So we have these phenomena, and this also impacts the reactivity of the particles. Therefore, the reactivity of the particle is directly impacted by the size. Now, in the slides that you present, I added like papers that I think could be very interesting for you to read. So for example, just looking back a few slides back, okay? These papers, you're welcome to just double click, and in your free time, you can read more about these properties, okay? Another important parameter is the colloidal dispersion, okay, which is also related to the size. So this is another parameter that is related to the size. So the electrostatic charge of a solid surface, okay, will attract counter ions and repel co-ions in the solution, okay? So this is a known phenomenon. When we have a nanoparticle or any particle in water, okay, according to the charge of the particle, it will attract counter ions and reject the similar ions, okay? So this is a very important phenomenon. So the co-ions will be rejected. The electrical double layer, as we see here in this in this figure. So this is actually, for example, the negative charged particles. It will attract the counter ions. So these are positive charge. And this layer, which is about 10 nanometers in size, is actually termed the Stern layer, okay? And beyond this layer, we see here a very interesting phenomena. So this is a fixed layer, okay? And this is the charge of the particles or the nanoparticles. And beyond this layer, we see a very interesting phenomena, which result in actual attraction of ions from the bulk solution, okay? But here we see also a mix of positive and negative ions, okay? And this is because the charge of this particle is actually a little bit masked by the Stern layer that is absorbed into those particles, okay? So negatively charged particles accumulate positive counter ions, okay, to satisfy the neutrality of these particles. A layer of cations will bind closely to the surface, and this is the Stern layer. Beyond that, beyond the Stern layer, we have also negative charges that still attract cations. So we still have here attraction of cations and ions. And these ions are repelled, but they're not repelled the same way that they're repelled within the Stern layer, okay? Because the net charge on this surface is actually not as negative as the original particles, okay? And then cations and ions will move until we reach electroneutrality. And this is known as the diffuse layer. Beyond the diffuse layer, we have here the bulk solution, okay? And the Zeta potential, okay, the Zeta potential is the electric potential at the hydrodynamic plane, which is this plane, okay? At the hydrodynamic plane of the shear. This is also the slipping plane. So the Zeta potential is measured actually here at this plane, okay? And why is this important? This is actually a phenomena which is very important because when a surface or a particle is immersed into aqueous solution, and in this actual course, we're talking about water and wastewater, and we will start to discuss more about the applications. But it's very important to understand that when a particle is immersed into an aqueous solution, it will form this type of interface, okay? And this interface is very important to understand all the phenomena that are happening. So for example, we can have aggregation of particles. And usually we don't want to have aggregation of particles. Well, it depends when, but usually we don't want to have aggregation of the nanoparticles. And therefore it's very important to generate the conditions that will allow the particles to be stable and not to aggregate. And eventually the distribution of cations and anions around the particle will dictate how the particle will actually be in solution, okay? So these phenomena are very important. And we also must remember that these phenomena happen in the microscopic level, okay? So they happen in the microscopic level, and the actual thickness and volume of the electrical double layer is extremely small, okay? This is a phenomena that also happens spontaneously, okay? It happens spontaneously, and I think that's about it, what I have to say about this. As I said, the zeta potential is a very important phenomena. And when we measure the zeta potential, so there are various equipments that we can actually measure the zeta potential. It's very important to measure the zeta potential with different pH values, okay? Because eventually the pH value also impact the amount of cations that we have in the solution. Therefore, we measure the zeta potential different pH values. And also, as was discussed before that, when we immerse a particle in water, we have the size of the actual particle. So for example, when we immerse titanium dioxide into water, we have the size of the particle itself, which could be about like 20 to 25 nanometer. But then we can have a layer of water that is actually attached to the particle, and it can give like the hydrodynamic diameter. So all these things are very important when we think or address the interaction of nanoparticles in the aquatic environment, okay? When we look at the values of the zeta potential, so when the zeta potential is about larger than plus 30 or minus 30, it is generally considered that that there's like sufficient repulsive forces to attain colloidal stability. So when we look, for example, and we measure the zeta potential, and we see that the values are either very high or very low, then we can assume that we have stability. But between minus 30 to above, for let's say to plus 30, but usually since the particles are negatively charged, we can assume between minus 30 to 0. We can, a smaller zeta potential value can result in particle agglomeration, okay? And flocculation. And this is due to the van der Waals attractive forces when the particles are actually near each other, okay? So these are very important phenomena. Now, how does this relate to application? And I will not, this is just a story that, a very short story that I will not tell now, but we will discuss this when we will talk about photocatalysis, okay? For example, this is a photocatalytic ceramic membrane, which is coated with N-doped titanium dioxide. Now, this is research that we conducted in the lab. And what we're trying to do in the lab is to take the basic science into application. Because when we think of smart materials, and there are tons of publications, but if we look at the amount of applications, do you have an idea of how many applied actual use of nanotechnology for water and wastewater? Did anyone like see practical papers? Well, if you scan the literature, okay, you will see that there's tons of papers, basic science papers that discuss or publish on the actual scientific use or the synthesis of various nanoparticles, okay? And they synthesize the material engineers, which I'm not a material engineer, so I'm a chemical engineer. They discuss the synthesis of these nanoparticles, and they analyze with all the different methods like they discussed before, the XRD, TEM, SEM, AFM, whatever, okay? So XPS, all these analyses are being conducted. They publish papers. Usually, most of these papers, they actually use some type of dye. It could be like methylene blue, rhodamine, or whatever type of dye. They use these particles in suspension. So we discussed about the colloidal stability and all that stuff, agglomeration, whatever. And they, for example, determine the sorption capacity of those particles, or the photocatalytic activity, or whatever. However, these studies, most of them are not applied in real life. And since our goal as engineers is to make an impact, we want to see how can we use this knowledge on nanoparticles for application in order to improve the quality of our water and our wastewater. And the applied-based research are almost none. So there is a huge gap, which I hope that some of you will solve, between taking the particles from the scientific studies to actual implementation. I can say that we had a study, and why I'm showing this figure, we had a study which is an EU, European Union project with many partners, okay? And me and my colleagues were from the applied side, and we had also a few groups that worked on the coating of the membranes, of ceramic membranes with nanoparticles. And they tested different technologies. So some of them were like sol gel, others were nanojet, plasma, whatever. So they tested different types of technologies and they coated the membranes. Now, they published many papers, okay. But when we try to examine what happens to these membranes in actual water, so we tested these membranes with dyes and with solar radiation, and we had degradation of the contaminants, either the dyes or the micropollutants. But, and this is like a very important point, when we immerse those membranes into natural water, we had a huge reduction in the activity and reactivity of those coated membranes. And this is because in water, we also, for example, have calcium and natural organic matter and magnesium and bicarbonate and all these things, all these water quality parameters. And this is, I think, what we want to most emphasize in this course, not to talk about the basic synthesis or of the nanoparticles or the characterization. We want actually to go to a different level, to the application level. So how can we take this knowledge and apply it to actually improve our water quality? So what we saw, to make it short, we also, I will also talk about this in a different lecture. We also had pilot studies. The colloids in the water actually clog these membranes, and also we had issues with fouling. We had issues with for example, calcium ion absorbing to the surface of the nanoparticles. So remember that we discussed, for example, that if the nanoparticle is a negative charged, and we have in the water here calcium. So the calcium, if it absorbs to the nanoparticle was not available to generate the hydroxyl radicals that we were interested upon irradiation with solar sun. And when we had water with higher calcium content, the phenomena was even worse. And so the idea here is to understand that synthesis of the particles is very important, but we also really need to emphasize the application. We really need to emphasize how can we take this basic science knowledge into applied, because our goal is to make an impact. Okay, so I will talk about this story, not now, and we'll talk about advanced oxidation and photocatalysis, just to show you how good intentions result in almost no impact or result. And then I'll also discuss how we try to resolve this issue engineering wise, okay? So what we try to do. In addition to that, this project was 3 years, and we were supposed to get to the applied part of the project within a year. But the material nano chemists, which I have a lot of respect to them, they wanted to test new nanoparticles, new nanomaterials, new coating methods, and blah, blah, and this and that. And we only in the 3rd year, we reached the applied status of the project. So we didn't have enough time to test the pilot phase, because the material engineers wanted to make the best catalyst, but the best catalyst did not work in real water. So this project kind of like had a huge impact on me, because I would say that this project did not lead to building the reactor that we wanted. Our idea was to actually degrade pharmaceuticals and drugs in water. And we worked with gray water and with surface water, and the project just did not work. We have a new project now that I'll be very happy to share with you. It's a German Israeli project. And now we're developing metal-based membranes that are coated with particles by using electrophoretic deposition. Where the actual probe is results in release of the nanoparticles that are coated, and the membrane itself is within the EPD system is being absorbed by the nanoparticles, and therefore we get like a coated membrane within the EPD system. Now, again, with this study, we really want to get to the engineering phase, and I always like urge my students, we don't want to have the best performing nano catalyst. We want to have a nano catalyst that will perform well in actual water quality. So this will be discussed further on, okay? We can also calculate the double layer thickness. And the double layer thickness, which is 1/kappa, and it's measured in Armstrong. When we see equations, it's very important to understand, like for example, in this case, Z, which is the magnitude of the positive or negative charge on the ion, the ionic strength. So the ionic strength is actually representative on the amount of negative and positive ions we have in solution. So when we try to develop a technology, and for example, in groundwater, it really depends the TDS, the total dissolved solids of the groundwater. So I was in sabbatical in IIT Madras in Chennai. I'm a visiting faculty there. And I'm sure that this is not new to you, but one of the things, it was like pre-corona. And one of the things that due to overpumping of groundwater, the groundwater became more saline. Now, assume that we want to develop a technology with water that has increased salinity or increased total dissolved solids, which results in a higher ionic strength. This actually makes, so the higher ionic strength, you can see here, will actually reduce the double layer thickness, okay, and result in agglomeration of those nanoparticles, and will render them insufficient. So therefore, the interaction between the nanoparticles, the science, and the actual world is very important. And this is a gap that we're talking about. This is a gap that we really need to solve to make something practical. So nanoparticles and nanomaterials are have a huge potential, but only their potential will be if we manage to design these particles and collaborate with people from different fields to the applied field. Okay, and this is a gap that we really need to solve. We need to think of smart reactors that use nanoparticles and nanomaterials, and to try to overcome these gaps. Okay. So there are also other parameters that are very important to discuss. So generally, the crystal structure of bulk material and large nanoclusters are the same, only little variation in the lattice parameters. For instance, bulk aluminum and 80 nanometer aluminum has the same face-centered cubic structure, okay? But there are exceptions to this. So for example, when we look at gold, it showed an FCC, a structure of 3 to 5 nanometer gold particles, which were icosahedrally, okay? So this was the structure of the gold nanoparticle compared to the bulk gold particle, okay? So with gold, it did change a structure to a polyhedron with 20 phases. Okay, and to conclude this part of and we'll soon continue to talk a little bit more about the aqua solution, the colloidal stability, the surface properties, the shape and the structure of the nanomaterials vary between the bulk material and the nanomaterials, okay? The surface area and the chemical reactivity are highly accelerated by nanoconversion. In additionally, some lattice parameters and changes in the geometry were also reported. So for example, with the gold nanoparticles, the melting point and the thermal properties highly rely on the particle size. So if you remember, we saw that we have a decrease in the melting point, okay? With decrease in the particle size. And also the electrical and the electronic properties of the materials can be affected by nanoconversion compared to the bulk materials. So it's very important to understand these things, and also it's important to find ways to apply these properties of the nanomaterials to solve things that are related to the aquatic environment, okay? So we will move on to discuss a little bit about aquatic environment. And I would just like to re-emphasize something about, I would say, about the significance of nanomaterials and the application, okay? So we know that, and it's already also discussed in the previous lecture, and I also discussed about how engineered nanomaterials, and you had a discussion about engineered nanomaterials, so they really attracted a great deal of attention, okay? And this attention can actually be translated to technology. So it's very important to find a way to translate the different properties of nano materials into the different applications. Okay, so this is, as I said before, this is a gap that is very important. How to make the materials into products, and products that work within the environment that these materials are actually implemented. So when we look, for example, and I think we discussed this a little bit about the properties of gold nanoparticles and their potential application. And this, as we said before, it depends on the size and the shape, okay? Colloidal gold nanoparticles have either an intense red color, okay? And this is for spherical particles that are smaller than 100 nanometer. Or it can have, for example, blue color for larger particles, okay? the scientific evaluation of these particles, and maybe the gold nanoparticles, did not begin. It started actually the 1850s with Faraday equation. And what we can see here is that this actually was known about 150 years ago, okay? So this phenomenon was actually known 150 years ago. Now, nanotechnology is very interdisciplinary, okay? And we can see that nanotechnology is relevant to material science, molecular biology, applied mathematics, physics, chemistry, and electrical and mechanical engineering. And what we're trying to do is we're trying to take these properties for application of nanomaterials in the aqueous phase. Now, one thing that we really need to understand is a few things, and we also always need to look at the big picture. And the big picture, when we apply nanomaterials into the aquatic environment, is the issue of the end of the lifetime, okay? So the LCA, okay, the LCA of the different processes should be also considered. LCA's life cycle analysis. So when we synthesize the nanoparticles, what happens to it at the end? Will it result in, for example, in contaminating the environment? Will it result, will the production result in release and exposure? When we use these nanomaterials, do we have any transformation phenomena occurring? So for example, we have in water natural organic matter, and this, for example, humic acid can coat the nanoparticle and result in different fate and transfer phenomena, okay, which will be discussed in the next lecture. And we need to think about the end of the life, nanomaterial life. And we need to think if we can recycle. So when we take nanotechnology into the aquatic environment, we must consider all these factors. We need to look at the big picture. Okay, I think that the issue of circularity is very important today, and therefore we cannot only synthesize the material. In this project that we're having now, we are testing different materials, different coating methods, and we have a group that is working with us that is actually looking at the global potential, and they're looking at the impact of the synthesis on carbon release. So for example, if we have two different types of nanoparticles and we want to coat membranes, and one of the nanoparticles is coated by electrophoretic deposition, and another nanoparticle is coated by sol gel, okay? And now we need to know which membrane to work with in order to degrade contaminants or absorb contaminants. Now, we need to look at the entire life cycle analysis, which means what are the conditions that are required to synthesize the nanoparticles? What are the conditions that are required to coat? Temperatures, pressures, raw materials. Are the raw materials available? Are they expensive? Are they cheap? Maybe we would prefer to take, and then we need to look at what would be at the end of the lifetime of this of these nanomaterials. Are we looking at disposal? Is it being disposed in landfill or open dumps? And then do we have leaching of those particles into the aquatic environment as a contaminant? So we started with a particle that served that served as a potential for having something good. We wanted to take these nano technologies and make something good out of it. But maybe at the end we had leaching of the nanoparticles from the membrane and resulted in contamination of groundwater sources. So good intentions that turned bad, and this is the tragedy of our environment. So we really need to think about the interconnections of the aquatic ecosystem. That's very important. And we need to think about all the transport routes, transport and transformation routes, either in the atmosphere or in the water. Okay, so we need to look at all these things, and we need to have, as environmental engineers, we need to think a bit more about the consequences of the application of different materials. Okay, so our target is not only to have the most efficient system. We need to understand the life cycle analysis, so these things are very important. And we will have also a lecture about nanoparticles, toxicity, and how it impacts the aquatic environment. So we will also discuss these things. And today, and we'll also discuss, for example, pollution. And so we will show two sides of the nanomaterials. One side is the beautiful, where these particles are amazing and they can serve many purposes. And the other side is the, I would say, the ugly, how they contaminate the environment and what happens to these things. So these are very important. We will discuss about the impact on the aquatic life, okay? Only very shortly, because our goal is to actually discuss more on the applications. So how can we apply nanoparticles onto membranes? So do we coat them on the membrane, or when we fabricate the membrane, are the nanoparticles part of the solution that is being used to generate the membranes? So there are many things there to consider. When we use nanoparticles, for example, as biofouling control. So what would we need from a nanoparticle to be a biofouling control? Should it, for example, coat water pipelines? But then what will it do? Would it like absorb the contaminants? Are we generating, for example, materials that maybe can absorb arsenic, for example? But they may be, so for example, maybe these particles absorb arsenic only on the particulate phase. And maybe the sorption capacity is at pH of 2. When do we have pH of 2 in actual water? So for example, if we have groundwater contaminated with arsenic, and in the lab, we showed that we have a high sorption capacity at pH of 2. But when do we have this actual pH in real life? So if the sorption capacity at neutral pH, or pH between 7 and 8, is very low, then this technology is not valuable for us. If the generation of the materials to absorb contaminants, fluoride, for example, in water, works only in the powder phase due to the high. So we showed that there is a high surface area for particles with a smaller size. But if we take these nanoparticles that work really good in the particulate phase, and when we absorb them, when we coat them on membranes, they do not actually perform, then we also have a problem. So I think that from my perspective, what we're trying to show in this course is the application of nanoparticles. We'll emphasize how nanoparticles can enhance advanced oxidation processes, how nanoparticles can serve as a medium to absorb contaminants, how nanoparticles can be used integrated into membranes, and maybe have like catalytic membranes or photocatalytic membranes, and also the fate and the transport, and looking at the big picture. So from my perspective, I think this is one of the most important features that I would like to discuss. I think that an issue of the suspension stability, as we discussed before, is very important. So for example, when we have, and we can go just show here, I think we discussed this and no need to discuss this. Okay, so what happens to the life cycle of the particles when they're in the aquatic environment, whether they reach landfills, and the contamination, for example. So are the sources of different contaminants? It also depends. So when we look at natural organic matter, when natural organic matter, for example, interacts with metallic nanomaterials, it can aggregate. And the hydrodynamic diameter of these metallic nanomaterials should be much lower in the aggregate stage. So this is very important. We discussed that the stability of the nanoparticles, and when we measure the zeta potential, we don't only measure the size of the nanoparticle, but also the hydrodynamic diameter, which is actually the water that is strongly bounded into the materials because of the aqueous phase. So all these things are very important. So the increased stability of the suspension. The bioavailability. So we need to make sure that that when we use nanomaterials, the bioavailability can actually result in contamination of the environment. And this also relates to the solubility of the nanoparticles. Okay, and we saw also that I'd just like to kind of summarize is we saw that the size has an impact on the surface tension, okay, and the solubility. So these factors are very important when we talk about toxicity of nanoparticles and their bioaccumulation in the environment. And also we discussed the electrostatic interactions of nanoparticles. And for example, even if we look at the interaction of nanoparticles with water, and we know that water has also biological, and water also has, for example, algae and bacteria and viruses. And most of the biological, I would say at the pH of the water, all the bioparticles have a negative charge. So then we need to look, for example, at the interaction between these nanoparticles and the bioparticles, and interaction of the nanoparticles with the natural organic matter, with the calcium in the water, and all these things that would impact the electrostatic repulsion or the attraction, van der Waals attraction between these things. And I think that I will probably end here, and I'll be very happy if you have any questions to ask. I also want to know, like, kind of what is your background? If most of you are engineers, maybe you can like thumb up, and just so I know kind of your background. Engineers? So most of you are not engineers?
Yes, engineering background.
Okay. Okay, so I think that, so I think it's interesting. I see that most of you are not engineers. So I think that it'll be very interesting to kind of look at the engineering side of, from biotechnology. Okay, so I see that a background comes from chemistry, biotechnology, let's see, okay. And few of you are engineers, okay. So I think the issue of the application is where the huge gap actually exists. And we will emphasize the application side of using nanoparticles and nanomaterials in the aquatic environment, especially for water and wastewater reuse. Okay, research called biotechnology. Okay, wonderful. Okay, wonderful. Does anyone have any questions or anything? I'm not sure about the timing, so I kind of like, I don't know about the timing.
Yeah, it is just 3 o'clock. 2 minutes past 3. Yeah.
Oh, okay, okay. Okay, so are there any questions? If not, it's okay. I think that
Yeah, there is one question in the chat box.
sure. Environmental science. Okay, so the question is why the electrical double layer is formed, right? Right. So,
Yeah.
Okay. So this is actually a very important question. And the reason that it is formed is because we have an interaction between the particle and the aquatic environment. So what happens is that when we have a solid surface, for example, a particle, or so it could be a particle, it could be a nanoparticle, it doesn't matter. When we have a solid surface that is actually, so when the solid surface is actually immersed into the aquatic environment, assume that the solid surface has a certain charge, okay? So most of the particles, like natural particles, have negative charge, okay? Now, in the water itself, we also have charges. We have anions and cations, okay? So assume that you're taking this particle, which has its natural charge, and this particle is actually submerged in surface water, groundwater, saline water, seawater, doesn't matter which water. And the bulk water itself also has charges, right? So water can have, for example, calcium and sodium and chloride and natural organic matter, and water also has other particles and colloids inside, okay? So when the particle gets immersed, the nanoparticle gets immersed into the aquatic environment, what happens is that, assuming that the particle has a negative charge, positive ions from the bulk water will attract to this negative charge, okay? And so they will attract to this negative charge and form a layer that is very thin, and this layer is about 10 Armstrongs, and it's called the Stern layer. So positive charges from the aqueous environment will attract to this negative charge, because we know that negatives and positives attract, okay? So they will form the Stern layer. Now assume that, I don't know if I have something to show. Assume that this is the particle and negatively charged. We'll have a small layer of positive cations on it, okay? Now, here we had, for example, a very negative potential. When we had the positive ions attracted to it, in this area, we have a less negative potential, right? Because the positive charge masks the negative charge of the particle. So now we still have attraction of positive cations from the bulk water, but it's a little bit less, okay? And we also have here negative charges because of this interaction, because we have less negative charge. So now we have like this negative charge. We have a Stern layer which absorbs the positive charges. Here we have also we have attraction of positive and negative charges. And this layer will actually extend into the bulk water until we reach electroneutrality. And the thickness of this layer depends on the ionic strength of the water. So if we have more charges in the water, seawater, okay, we'll have a very thick layer. Why? Because in seawater, we don't need to extend a lot because we have tons of cations and anions. But for example, in groundwater, maybe in surface water, groundwater, we have also a lot of a lot of dissolved solids. But for example, in surface water, where we have, for example, water with a low TDS, this layer will extend a lot until we reach electron neutrality because the bulk water has less positive or negative ions. So this is kind of like kind of a way to explain what happens with, and then we can also measure the thickness of the double layer. Okay, we can measure it, okay, by 1/kappa, which gives us the thickness of the double layer, which really depends on the ionic strength, on the diameter of the particle, and also other different types of parameters. I think also important is how we measure it. So we measure it by Zeta Potential, okay? And Zeta Potential actually indicates the degree of electrostatic repulsion. And what else do you want to say about this? Oh, and the values, and the value of the Zeta Potential. So if you measure the Zeta Potential of a particle and you get like values that are below -30, for example, then it means that the particle is very stable. It will not tend to aggregate, okay? But if you, for example, get a Zeta Potential of, I don't know, -5 millivolts, then it means that the particle is not very stable. So it would more tend to aggregate. The same also with the positive charge, by the way. So the particle could be either negative or positive. So if the particle is like positively charged and we get above +30, it means that the particle is very stable. And when we get the closest we get to the zero potential, means that the particle is less stable. So I think kind of that's about it. And also there's a lot of material to read about it. If you want, I can really find a good material. And there is also a book, a really good book on water treatment that has a beautiful chapter on all these things. And if someone wants me to like send material on that, then just please inform me and I could do that. I think I tried to make it more try to explain it kind of in a more way that could be maybe more clear. Was that clear, I hope, Subash?
No, the question was from Smriti Joshi.
Oh, okay.
Not from Subash.
Okay, sorry.
No, she's.
Okay, I don't know. I just saw the name Subash in the chat and I said Subash.
Yeah. Now she has texted. Yeah, she is fine now.
Okay.
Professor Hadas?
Yeah.
Yeah. Can you throw some information on octonal and the water partition coefficient with respect to the distribution of nanoparticles? So how far it is affecting the accumulation or bioaccumulation factors?
Okay, can you repeat again? Sorry.
Yeah, based on the octonal and the water partition coefficient of the nanoparticles, how it is affecting the system of bioaccumulation towards the toxicity profiling. Because once we think about the toxicity levels of these nanoparticles in aquatic systems, how far these values like KOW value or octonal air coefficient value, how far these things are significant towards that?
Okay, so when we look at these coefficient values, it's a real simplification of reality, but we try to make things simple in order to understand. So, for example, like we have the coefficients, for example, the KOW, which gives us an indication of, for example, if we have like water and alcohol, where the particle will be in the water phase or the organic phase. And for example, when we have the Henry coefficient, it gives us an indication, for example, if the contaminant will be dissolved in the water or in the atmospheric phase, right? Because the coefficients are actually a simplification. So just, I'll go back to the bioaccumulation very soon, but for example, when we have, for example, material in water, and we want to know, for example, if we look, for example, at phenols, and we want to know if the phenols will dissolve in the water or if they will evaporate into the atmospheric phase. So we have this kind of coefficient that tells us how much this material will be in this phase versus that phase, and there's always an interaction. The same with bioaccumulation. So we have tissues, fatty liver and stuff like that, which are actually lipids. And we want to know, for example, how much this nanoparticle will bioaccumulate onto those. So we have onto these fatty tissues versus streaming in the aqueous phase. So these bioaccumulation coefficients are really simplification, but we use them in order to kind of get an understanding of where the contaminant will be. Will they be absorbed and accumulated in fatty liver? So we know, for example, that, like, for example, with DDT, we know that it, for example, can bioaccumulate, and we have like this bioaccumulation where in the water, we can have concentrations of nanograms per liter, okay? And then when we reach, for example, higher organisms, because it bioaccumulates, we can have like a concentration of ppms in higher organisms. And so when we have like more bioaccumulation, there is a chance that higher organisms, like if we start with the concentration in water and we go through higher organisms, if it's bioaccumulative and the coefficient shows that it will bioaccumulate in the fatty tissue, then it will reach, for example, fish, humans, and stuff like that. And so, but we really need to remember that these bioaccumulation coefficients are really a rough estimation, because they don't consider fate and transfer phenomena. For example, they would less consider phenomena as sorption of water constituents to these particles, oxidation reduction interactions, and dissolution, aggregation. So we can use these as kind of a way to guide, but we should look at it very carefully. Like, for example, with mercury and stuff like that, it doesn't really give the entire picture. It just gives an estimation. Okay?
Yeah, thank you. Thank you.
And we will talk about this also a little bit later, because we do have a chapter on toxicity effects and stuff like that. So this will be discussed more later on.
Sure, sure.
Yeah, there is one more question, Professor Hadas. The relationship between zeta potential and photocatalytic efficiency.
Zeta potential photocatalysis?
Now, what is the relationship between zeta potential and photocatalytic efficiency?
Okay, so first this question, and actually I have even slides on that. We will talk when we'll discuss advanced oxidation. But it has a huge impact, because the zeta potential of the particles, what for example we found in our study, and we were like, I would say, depressed in some way, because we that due to the zeta potential of the nano catalyst, it resulted in absorption of water quality constituents. And that actually resulted in that actually resulted in a situation where in real water, in the aquatic environment, the technology that we developed did not work. So and also what we found is that with water with higher calcium content, it resulted in less efficiency of nanotechnologies that we tried, and less than magnesium, okay? We found, for example, that natural organic matter, and it depends on the type of the NOM, also reduces the efficiency of photocatalysis. So all these, I would say, all these things actually had a huge impact. And we will discuss this a little bit further also during the course. But the Zeta Potential, and not only the Zeta Potential, and maybe I'll just add one more thing that we will also discuss later. It's the streaming potential. So because we took, so for example, we took membranes, and let's say this is the membrane, and we coated the membrane. And it's also important to look at the streaming potential, not only the Zeta Potential. The Zeta Potential gives you the potential of the particle itself. But if you want to also to understand the potential, the global potential of a membrane that is coated, then if you measure only the Zeta Potential of the particles by themselves, it will not give you the entire picture. And therefore you need to measure the streaming potential, which is actually the potential, which actually gives you the potential of the membrane pores. And actually you stream through the membrane water with different ionic charges, okay? And it gives you like the global potential of the entire membrane. So it's not only the Zeta Potential, it's also the streaming potential, which gives you the potential of the coated substrate, okay? Whether it's porous or not. And we will also discuss a little bit about that later, because Zeta does not give you the entire picture. You need also to measure the streaming potential, which is the potential of the coated substrate, either if the water streams on it or if the water streams through it, okay? Because the pores of the membrane, they also have a potential. So when you coat a particle onto a surface, it's not only the Zeta, but this is a very good question. We will also discuss a little bit about that later. Okay, I hope I did.
Yeah, Hadas, yeah. I think if there are any questions, then still you can drop us. I think most of the topics that the question was asked, I think it will be covered in the forthcoming days, I feel.
Yes, yes.
Relevant, yeah. So I think
I hope I didn't steal the break, the students' break.
Yeah. So I think we can stop here, and Professor Dr. Ram is also here. I think he can take the lead, and then Hadas, you can just make Dr. Ram as the host. Then only he can able to share the screen.
Okay,
thank you.
With pleasure.
Yeah, thank you. And good to hear to Dr. Barney and Dr. Hadas.
Yeah. So
I just missed out the morning session of Dr. Barney, and I had a chance right now to sit and listen to the YouTube video of it.
Okay.
And parallel to Dr. Hadas, I think you both have done my job.
Okay. So, okay, participants, now we have with us Dr. Ram Sundaram, where he will be taking us over the conventional water treatment techniques, the advances that it has went through, and the application of nanomaterials, especially in water treatment. So here we will be having a background knowledge of what was already there and what is currently under nanomaterials. So over to Dr. Ram, sir, and then you can kindly take the lead.
Yeah, thank you. Thank you, Dr. Barney. And Hi to all the participants over here. And I just went through all your questions and here to Dr. Hadas and Dr. Barney. I felt like they have given a lot about nanomaterials, and now my job is pretty clear. To give you only onto the application part of the nanomaterials. I'll try to stick on to it. And being the later part of the presenter, I understood like I should keep up my time and make sure like your day ends smoothly, right? With the question of what next for future. So here comes, yeah, I'll go to my presentation now. And to disclaimer, I'll say to all the participants over here, it's like I'll be taking you through 10 slides. So don't worry about sitting for one more repetition of nanomaterials. Here, my presentation will be more towards application part of it, and application to the water treatment, and how far this nanomaterials has found its part. And I'll also take you an interesting part like a small scale lab research, how it has been commercialized today. I mean, the path of commercialization. A patent has already been on the process of filing, and the product development is already on the almost done. 80 to 90% of work is done, and probably it will be launched in the market by the month of March, which will be used for wastewater treatment, or in other words, I can say reclamation of treatment. So I'll take you through the path of application oriented. So that will be the target of the presentation. And to start with, or to stick on with it, from morning you are hearing to nanomaterials. Various kind of nanomaterials has been introduced by Dr. Barney, and it's the size and volume and interaction phenomena, all things has been covered by Dr. Hadas. So let us start with that funda of interaction phenomena of the particles. So when you take any water treatment, the interaction process like adsorption, chemical reaction, catalysis, those things are the major part of conventional water treatment, which takes care of it. And first and foremost, conventional water treatment to our knowledge is the coagulation part, where the positively charged ions attract to the negative charged organic material. This was the last question which has been raised to Dr. Hadas, why nanomaterial has a double coated layer. And here it starts from our original conventional water treatment. Every particle has anion or cation reactions attached to it. And the classical coagulation method, what it tries to do is the moment you add any positive nurtured ion into the water body or water system, it tries to attack the negatively charged, and during the process of detention time, it gets flocculated and settles down. And the well-known ions which have been added for coagulation is one is ferrous sulfate, another one is aluminum sulfate, which found its application too much. So if that is the case, why this nano? Right, that's the question which came into it. The problem with conventional water treatment, especially into coagulation, is yes, it is very good at coagulating the organic material. What about the inorganic material? A few traces can be coagulated. What about the bacteria, protozoa, or viruses which are present in the water? That's a question. And one more drawback of this coagulation is post-treatment, you will have the traces of aluminum or ferrous in the treated water, which may be a toxic, maybe toxic to the environment, maybe toxic to the human health, or any other consequences it may create. And we call this phenomena as leaching in terms of environmental concepts. So when you have this phenomena, what next can be done? Whether there is a possibility of going for filtration. This was the second sort of development of treatment, right? Filtration. And very well-known fact of treatment starts from your slow sand filter, then we had rapid sand filter, then ultrafiltration, then you have microfiltration. Then it goes to the last part of reverse osmosis. Nanofiltration, let us come to the in a later stage. So what is actually happening is, like when you take a slow sand filter in conventional water treatment, the performance of slow sand filter was equivalent to ultrafiltration. But only one drawback is the flow velocity is about 0.1 meters per second to 0.1 meters per hour to 0.3 meters per hour. So that made very slow process. And during this process, in order to make sure there is a microbial reaction that removes the organic content, what happens is like they create a biofilm on the top of the sand filter. And once that microfilm or biofilm is activated, then the process starts. To kick on the flow process, then came the rapid sand filters. And the process, once again, here is the mimic of the same, but it's a pump system, right? Where the energy has been supplied and there's a rapid flow of 25 meters per hour. So this is the depth of water flow that can be handled, and the performance was a little bit lower compared to slow sand filter. There comes a microfiltration. The microfiltration handles up to 0.1 nanometer size, pore size was there, and it is able to handle or filter up to the organic and inorganic materials. And when you say about bacteria, it was it was not adequate enough to handle the bacteria part of it, and naturally don't handle the viruses or multivalent ions or monovalent ions. It can't filter it. And to overcome this drawback, then came the ultrafiltration, where you had 0.01 nanometer as a size, and which was capable of handling this multivalent ions, and it is able to filter up to it. And reverse osmosis, which was an ultimate which has been called across till today, which can filter multivalent, monovalent ions, including bacteria and viruses. The problem when you associate here is, one is the energy that is required and the infrastructure that has to be created. So these are two things that make sure are hinges of application of conventional water treatment. So in conventional water treatment, still today, you can find a lot of reverse osmosis plant that is running across. When you take in your local locations or anywhere, you can find a lot of reverse osmosis plant that has been occurring. And to increase the performance of the reverse osmosis plant or any of these filtration methods, there will be a first step of coagulation that will be taking place. So it's a combination of coagulation and filtration. Now it is doing a lot in the industry, especially into the water treatment. Now the questions comes here is whether these treatment or filtration can do a selective removal. For example, if I want to remove only the chromium, whether it is possible, how far it is efficient enough to do the selective removal. That's the first question that comes into mind. The second one, if that selective removal is done, what is the associated cost or infrastructure? How much energy it is going to consume? That's the second question that comes into mind. So these questions look for the alternate technology or alternate application field into the nanosciences. This is one side of the story. And let's go to the next side of the story as a perspective of application of nanotechnology to, or not nanotechnology, conventional technology to water treatment. Being a researcher or being a person of concern on the efficiency, if you see any treatment system, we'll just worry about how far it is efficient, how far the pH has been balanced, how far this has been achieved, whether the chromium or the desired chromium has been removed or desired arsenic has been removed, and what is the quantum of temperature it has been maintained. So we are all worried about the efficiency of the system, but the other things that comes into picture when it's going to be a practical application or real world implementation are the quantity of water that is going to be rejected, what is the energy that is required, what are the environmental impact it is going to be creating, and what is the cost associated. Whether this cost means the cost of the system or cost of impact it is going to create, it is up to the decision maker to look out. So these are the perspectives that makes to look for a new implementation. When I see the efficiency part of it, reverse osmosis stands a big role as of today. And whether it's a desalination plant or whether it is going to be a commissioned domestic water treatment plant, the reverse osmosis finds its major role. But when it comes to the cost, this will be the last technology everyone will be looking after. And when you take about the rigid quantity that has been made as a brine solution, it has a lot of concentrated contaminants or pollution inside it. And when you see about the energy consumption, whether you have a filtration, there is a concept of filtration, like we can have all the filters in a system. Like you have a activated carbon, then you have ultrafiltration, then you go for a reverse osmosis filter. The moment you have the number of filters into picture, the power required or the energy to be supplied is higher. So this adds to the cost of the system. And there's a saying like the more complicated the system, the more is the efficiency. And when you have seen from today's morning 2 lectures, you might have seen like the nano composites have a better efficiency compared to a single nanomaterial. So complex, because some unexpected remarkable changes will happen than what is expected. So the same system comes into a water treatment system, I mean water treatment processes also. So these things makes us to look for a new thing, new measure of whether I can reduce my cost. That's the first one. And second one, whether I can do a selective removal of the system. When I want to make a selective removal of the system, now I have to look for nanoparticles, because nanoparticles have a specific target, like, I mean, it's capable of doing a specific target level removal. And when you say nanoparticles, the nanoparticles originally US EPS classified into 4 major systems. One is carbon-based nanoparticles, next one is your composite materials, and the third one is your dendrites, and the fourth one is going to be a metal and metalloids. Let's take the carbon-based nanoparticles. The carbon-based nanoparticles, they're well and foremost what we have seen in water treatment is activated carbon. Knowingly or unknowingly, years before we started this activated carbon, which has a surface area of 500 to 1500 meters square per gram, right? Irrespective of our knowledge, it has been started years before. And activated carbon, the only problem with the activated carbon is, even though it has a surface area, the kinetics is very low. It means what the reactive time it takes is more. So you need a big detention time to achieve the kinetics, I mean, to achieve that activation rate, and then the treatment starts. So this artificial nanocarbons, or so-called graphites or quantum dots, all things is like we are improvising the kinetics part of it. We are improvising it reactive content of it. So the first and foremost is the activated carbon, which came into the picture. Then the widely used nano size particle are trichloroethylene, and which has been one of the paper which I've quoted in 2017. They have gone to the next level, like reduced by nanoscale zero valent ion, right? So they are trying to use this trichloroethylene for water treatment, reduced form, to remove the chloride content of it and chromium content of it. And it has found its huge application in the groundwater treatment. Groundwater, when you use the groundwater as a resource for survival, then if you have a very good chromium or the chloride content is very higher, then this trichloroethylene, they have quoted like it has been very good for this application. And trichloroethylene, not only in 2017, it has been claimed, and it has been for a while, right? And this is for groundwater application is concerned. It has found its huge implementation. Coming to basically, whenever you take a water, the water has a bacteria, protozoa, and viruses, all those stuffs. And silver, to our knowledge, it has a very good antibacterial impact. Okay, so silver has been nowadays, not nowadays, it has been a decade. It has been used for as one of the nanomaterial doped into the other TiO2 or TiO2 to absorb the antibacterial, right? To stop the foul smelling or to prevent the bacterial growth that is happening, right? And quantum dots is a zero-dimensional carbon material, nanomaterial that has been used for removal of, or for the treatment, or to say like to have a adsorbent phenomena, right? And there are other nanomaterials which are quite available in the field, like palladium nanomaterial is there for removal of mercury, and you have gold nanomaterial. So kinds of nanomaterial are higher, because I mean this choice of nanomaterial for application is based on the purpose of your treatment, what selective material or selective component you want to remove from the water. So according to this, the choice of the nanomaterial changes. It's not a universal norm. The same nanomaterial can be used for everything. So that was the point I'm trying to put over here. Okay, there is a nanomaterial right now. I have taken it and I've dissolved in my water, and let's say there's a very good absorption has happened, and there's a quite, either it has been settled down or precipitated. What's the problem? Major problem in the implementation is when you post application of it using a nanomaterial, there are two major issues that comes into picture. One is the separation part of it, and the next one is recycling after use. The separation in the sense you have dissolved a nanomaterial into a water, as Dr. Hadas quoted, you have used a nanomaterial for treatment, and the moment the nanomaterial has been used, yes, there is a treatment has occurred. Whether that nanomaterial is present in the discharge effluent, if you check it, yes or no, there is no question. You can't separate it, right? If you dissolve it, because it is a very smaller in size. And based on your specialization, I understood like most of you are from biotechnology and chemistry background, you can understand the size of the particle, how much it is. The size of particle is very difficult to separate. And if even though it is missed inside, what are the ill effects that is going to cause is still unexplored. To overcome this, there came the nanoporous materials. As I highlighted already before, the nanoporous material, one of the material which is well known fact is the activated carbon. The other well-researched area and which has been proved to be very effective in water treatment is graphene. The forms of graphene, 0 dimension, 1 dimension, and 2D and 3D dimensions of graphite. Graphite has been used for water treatment widely. And when you take graphite, the original form of graphite, it has been, as I said by Dr. Barney, they use manual milling. Right, they do it and they get the graphene across, and that graphene has a property of getting dissolved. To overcome that region, that need a multiple layer, and that multiple layer is being brought down by graphene oxides. And still, it has been further to make its stability. There are resins that has been put into place to make a graphite 3D, right? And that serves an industrial purpose of doing the treatment process. And graphene, when it's been used for water treatment, the major thing that has been observed or the coated is like it has very good property of absorbing the interaction phenomena, like microbes or viruses or pathogens and even heavy metals. Whatever is there, it is able to absorb it. What is the ill effect that has been created is the leaching part of it or the corrosion part of it. The graphene gets corroded over the time. And if it has been corroded, that material will be available in the effluent and it is still toxic enough to go ahead. Almost I have come to the last 2 slides, but that will take time to explain. So the purpose of here to go do this level is, if you feel like the conventional treatment was not able to capture your bacteria, virus, or protozoa, or monovalent ions or multivalent ions. And even though it is able to capture through filtration, there are a lot of energy requirement. So to overcome that energy requirement or the infrastructure, you bring the nanomaterials or nanoporous materials here. Nanomaterials get washed away. So nanoporous material, the membrane is, the material is of a bigger size, so it can be separated from the solution. Or post-treatment, it can be separated and there is no leaching. Even though the statement says as the days goes on, there is a corrosive property. And there is one more area which has not been yet researched that much is M-xynin, which is nothing but your nanomaterials of the forms of metals and metal ions. Or in other terms, it's carbide and carbide oxide forms. It's called M-xynin, M-X-Z-E-N-E, which has not been researched further into the water treatment. And those participants here, you can look out at and you can try your hands in M-xynin. And this thought made my lab to look into whether it is a form of iron oxides or metallic forms can be used for water treatment. This was the initial that went into the mind, whether there is a possibility of using metal oxides, right? Iron oxides into it, because iron oxide is not much toxic compared to the graphite. That was the quoted research from the health journals that has been quoted. So taking that into the, I've not done the toxicity study yet. We have to do the toxicity, the thing is. So with that thought, why should not we try with iron oxides as a nano material to treat the water treatment, like to remove the water impurities. That was the thing. And iron oxides, it has been quite well researched in case of textile dyes as a bigger particle, not as a nano level particle. So this was the coining term that came into mind, whether there is a possibility to use iron oxide for two reasons. One is, yes, nanotechnology is very good. The second one is graphite, which has been widely used across, has a property of getting corroded, and that can be a toxic element. And graphite is quite costlier, and you need to make a 2D layer or a 3D layer to have a very good performance. And the stability of the 2D layer or the 3D layer is based on the resin that has been used across, which has been used for capsulating or making into a final layers, or making one layer to the other layer, and you have a resin in between. If that resin is not working proper, then it is going to get dissolved. So this is what from the coated literature has been understood, and we tried in our labs to have mono layers of graphite and just tried it. The performance was very good. Initially, when we tried with graphite, it was the surface area was somewhere around 2,600 square meter per gram, and it was able to treat the water up to the desired level. There was a question asked, like, what level of treatment you do it? I mean, how you measure M or XRD to understand the layer. And I'll go into it during my prototype model. In next 10 minutes, I'll come to that. So you have a graphite layer that was doing it, and the moment that the resin is not stable, what happens? It gets leached up. There came the idea of going for iron oxides. Okay, so iron oxides, which format it can be used? Whether I can use that iron oxide as an absorbent, or I can use it as an oxidation agent, or a reduction agent, or a nanomembrane within the nanomembrane. This was a urge that made us to look for what is the water treatment application it can be done, how effective it can be made. When it comes to adsorbent, it's nothing but a format of we tried iron oxide initially, then go to the adsorbent. We tried the iron oxide as a coagulation material, nano iron oxide, or adsorbent material, a powdered form of it. A powdered form of it, we mixed with the textile dye, azo dye, to be precise, azo dye, and we went for the treatment. And we understood, like, yes, it is there, but how to separate the azo dye and also the dissolved iron oxide? That was a question that came into mind. And we are not damn sure, like, whether it is available in the treated treated water. So that's the second question. When there is a question of it, then we went for taking this material and we subjected to EDAX and ICP-MS to understand what are the elements that are present. Why we need elements? That's a question that came into mind. The elements will give you any changes into the water. If there is any additional element has been added because of any additional formation has come out because of your nanomaterial. To understand that, we just went for it. And we found, like, yes, there is a leaching has happened. We cannot say it as a leaching. There's no proper settlement. Still, we find as iron particles that are present inside, and it seems to be cost effective too. If it is going to be used for either soil irrigation or it is going to be used for any industrial repurpose, we have to remove that iron content because it is higher in ratio. So what is the next format of it? That was the second thought. And we just tried with oxidation, nano oxidation, where we have developed the Fenton-based AOP process. Fenton-based AOP process was very good in decolorizing the azo dyes, and it was able to make sure the hardness is, it was able to make sure, like, there is a proper treatment has happened and the water is soluble, usable. What is the problem there? It came as the ferrous ions got populated too much inside. And to eradicate that problem, can I use a nano iron particle as a carrier or a catalyst to do this process? Yes, we achieved that by making nanoporous material, and then we use metalloid, to be precise. It is a metalloid that has been used here to enhance the process. When I use the metalloid, we found, like, it is contributing additional ferrous apart from what has been added. because the metalloid has the ferrous property, which is giving an additional efficiency part of it. Still, there is a problem of leaching. What needs to be done? That is a question that is always right. We are working here to understand how to make sure the treatment is effective. At the same time, it is not affecting to the environment, or it is not affecting to the nest process. So this is the content of discussion. Then we went on observing like how is this process is happening, whether it is efficient or not. Yes, the process is very efficient. It shows like the treatment is very good, but the azotize has been removed and the water is usable. I mean, water is pure. I mean, it's decolorized and it has all the properties, but it has very good concentration of ferrous inside. Even though you have used the nano metalloid inside it, it has very good concentration of ferrous inside. So the classical test that has been done across is all the 14 variables, whether it is usable or not. Then we went for the elemental analysis. We found like a lot of new elements has been removed, lot of new elements has been added into the system. Now the thought process is, yes, let's go for nano membrane. What we did is, the usual thing in the membrane process is always recommended as the reverse osmosis, because they feel like reverse osmosis, you remove all the particles and the efficiency will be very good. As I started this presentation, I was saying to you, right, we are in a stage of reducing the cost, because we need every system to work without additional power supply that should be happening in the terms of sustainability. So we thought of utilizing forward osmosis. When we want to use forward osmosis, the powers cannot be supplied to it. So it means what? We have to coat any material onto the membrane. So every membrane is made up of polyamides. So we thought like, yes, along with polyamides, let's go with a material that can be coated along with polyamide to make the filtration efficient. So the polyamide has been coated with nano iron oxides, and it has been subjected for filtration. And the moment we started getting the results, we understood like, yes, the membrane along with nano coated, polyamides, nano iron oxide coated polyamides are working very good in forward osmosis itself. But the process is very slow. The process is very slow because the penetration is based on the depth of water that has been retained in the upper reactor. So this is the content of discussion. So this made us, why should not we dig on to the using this membrane, polyamide membrane coated with nano iron oxide for a use of a small scale wastewater treatment plant, where the water can be reclaimed and it can be used for other purposes. And the thought process was, usually the wastewater treatment plant used to be in a bigger scale of half an acre, or it will be a quarter of a container size. And now the question which came into my lab and the thought process is what? Whether it is possible to make a treatment plant which can handle 300 mld, 300 liters per day. Not mld, it's a liters per day. Whether it is useful, whether it is possible, since we have nano coated membrane, whether it is possible to do it. That's the first question that came into mind. And there was debate that went on. It is not possible to go on, and your material will not be stable enough. Your iron oxides may leach into the membrane. Your membrane will get choked enough. And there came the research of this, and now this product is ready. I'll go into the stage-wise story of it for the next 15 minutes to make you understand what happened. So this is the actual, the synthetic solution which we started, and this is the actual solution of the wastewater that has been taken. And then we went on with all this iron oxide formats as an absorbent, as a membrane, as a advanced oxidation. And we found, as I said, we found like the process is very efficient in terms of polyamide coated with nano iron oxides. Now there is a question like iron oxide may be a toxic and what will happen. And there are two things we observed during the process. One is like when we coated, there was a microbial growth in that membrane. And what to do was still is a question. And based on the research, search for research, we understood like we have to coat one more hydrophilic layer that will enhance, that will reduce the process of bacterial growth in that area of interaction or interaction between the membrane and the water. So this is the case, and this is the actual the post the membrane. We have taken a sample and subjected to SEM, and there was a question asked, what you infer from the SEM? Damn sure when I saw the first SEM analysis, we just inferred the particles, how it has been arranged, where are it has been arranged, whether the structure is very useful or not. And this is at a macro level. At micro level, what we are able to synthesize is whether the element is present as per the scale, whether the pitch is very clear, whether there is any leaching of the layer, it is visible in this. So this was the first analysis that has been done. Once we are damn sure about it, then we customized our treatment system into a small box kind of thing. Where the small box kind of thing, the entire assembly is being made with an assumption like we are going to do forward osmosis. We are going to do a forward osmosis. We are going to ensure like it has a nano coated material inside, which is going to do the process of treatment, and it is going to give us water which is free of arsenic and chromium. That's the reason we have went for iron oxides. You may ask like whether arsenic or chromium will be there in a wastewater. The kind of wastewater what we have dealt across for initial analysis and where it has to be deployed has the content of arsenic and chromium. If there is no arsenic and chromium, if you have mercury, then iron oxides may work or 100% may not work. That's a caution for a researcher to look on. The purpose of what material to be removed or specific target material to be removed. So that is the content of selection of iron oxide. One more. If you are not doing with iron oxides, I will recommend you on palladium, where you can try that palladium PD, right? PD you can try and you can get it done, right? Or you can use any carbon or carbide forms of benzene to do this process. From my experience of this trial and error method of choosing what nanomaterial to go ahead for water treatment, I found nano iron oxide, zero valent nano iron oxides will work better. And the material what we adopt is whether to go ahead with a 2D material or a one-dimensional material or a 0D material. At the initial state, we went with 0D, that is a powder format. Then we went with the layering material. And layering material, how we did it, which is a composite layering. It's not a particular layering. It is a composite layering by polyamide. Over that, it has been iron oxide has been coated across, and that has been subjected to the treatment mechanism. I hope the content is very clear, and you should not take as a researcher like iron oxide is a better one for doing the treatment against graphene. It is about the selective removal what you are doing. In other words, I can say like it is like a kind of imprinting, right? What molecule you want to remove it, you imprint that and you capture that and you utilize into a process. Okay, sorry. Before going to thank you, I have further 5 to 6 more minutes to speak on this. Coming to this, why you need a equalization tank, right? Basically, the nanomaterials as it's coated, it works on an acidic media. And bringing an acidic media is creating a system for response of the nanomaterials. Without that acidic content, acidic nature, your nanomaterials process is not working good. So we just made, this is the chamber where your entire content is going to happen, or nanomaterial content is going to happen. And this is where we control the pH. Without pH control, this entire process is not working good. Whatever you say, like iron oxide is working good or graphene is working good, is all dependent on the temperature and the pH what you are operating on. So it's a customized size of a reactor which we develop, and this balances the pH first, then it equalizes the temperature. What is the temperature equalization here? We maintained it is about 26 degrees Celsius, but it is damn difficult to work on. But we found a range like 26 to 32 degrees Celsius. This performance is it's almost okay. Like how we measure performance? Performance is measured as usually the treatment, selective treatment of particular element, and that has been measured using EDOX. And if you want in further to understand which material has been removed, what is the quantity of the content is to be removed, it is using the ICP OES. that has to be deployed to understand what is the quantity of concentration that has been removed or it has been additionally added. EDAX will give you an idea about what is the elements that are present, not the forms of element. That is also very required, because the forms of element make sure whether it is hydrophilic or hydrophobic in nature. What it is going to do here is the quantity lumping up, or so-called accumulations. So that is going to happen over here. So iron oxide based membrane has been fitted over here, and it has been allowed to treat, and the sludge has been taken out. The sludge has been once again recapitalized, and the quantity of sludge that has been created is almost manageable, like about 300 liters. What we have done till today, we have found like it's about 0.5 kilo to 1 kilo sludge has been created, and that has very good, or I can say in very rich of all the minerals, and you should find a way to dispose it off, right? And there's when you ask whether there's a leaching post you have coated with a polyamide, no. To our understanding, it was not a big leaching has occurred, and that has not been enormously shown in EDAX or ICP OES. So this is the concept, and this reactor, which has been developed in the lab right now, it has been in the process of getting productized or commercialized to do a minor setup of 300 liters per day using nanomaterial iron oxide coated membrane. And I'm not able to give a lot of particulars because still the pattern has not been awarded. So I'm just giving a grasp out of it, what we have done across. And when we had over here the nanomaterial at this point, this nanomaterial is stable enough. When it comes to nanomaterial, two things that has to be asked. What is the lifetime of it, right? The membrane lifetime. And we have found like there is a possibility of choking of the membrane because of small particles getting attached to it. There's no self-cleaning type. And when we try to give a self-cleaning velocity as a backwash, the nanomaterial is getting detached from the membrane. That is the second consequence we found here. So we have not yet still cleared onto the part how to do it. During that part, I have understood and I have just sharing with you all MXene, right? What I said before, MXene, which has a capability of storing energy within it. That nanomaterial has a capability of storing energy within it. When the energy is being stored inside, it can create a temperature difference, and that temperature difference can kill your microbes, and that can mean create or it can create increased lifetime of your nanomaterial coated membrane. So that is one way forward direction which I look forward to create in future, like how to have a self-cleaning membrane which takes care of or which increases the lifetime of the product. So this is one. So to give you back exactly, I planned the lecture for 40 minutes so that I can have a discussion, but I went for 45 minutes. So I'll have conclude in 2 minutes so that we can have a discussion on this product if you have any doubts. To give you back, what is the summary of it? When you want to apply for water treatment, the nanomaterials, you have to be very specific of what material I want to remove it, what molecular thing I want to imprint on it, which one element I have to be selectively removing on it. That will give you the kind of nanomaterial that should be used across. And many researchers make a mistake, like they go for a common nanomaterial for everything. That is one understanding which I came across during this entire period of product development. The second one is like which pH you are going to deal across your nanomaterial, and what form of nanomaterial you are going to deal across. Are you going to deal a nanofiber? Are you going to deal across with a 0-dimension nanomaterial, or a 1-dimension nanomaterial, or 2-dimension or 3-dimension nanomaterial? Whether it is required for your research, and whether do you have interpretation of what are the tests that has to be performed. There are two kinds of tests that has to be performed. One, to understand how your material is made up of, or how your structure is made up of. That is the test that has to be performed. On the second part of application, on application end, you have to see what are the elements that are added in, or what are the elements that are removed out of it. Okay, and if you see here, I don't know whether it's a statistical correlation, right? It is not an actual value. This oil and grease, it's not expected by us. This oil and grease here, it was about the initial effluent was 1, right? In a statistical analysis, that is highest value. The moment we just inserted a nanomaterial coated, polyamide coated nano membrane, suddenly it disappeared. This is not expected by us. We have never predicted this. We never understood what happened here, what actually happened here. And when we started looking on the chemistry part of it, why this happened, still we need to explore it. What I'm trying to say here is your complex nature of nanomaterial gives you wonderful research. Sometimes it gives you expected, sometimes it will give you an unexpected results. Because this is not our selective material. We are not worried about this oil and grease. We are more worried about arsenic, which I have not shown here, right? Arsenic and chromium I have not shown here, right? But that can be interpreted here from here, this point of view. Right, and this was not there. Total residual chlorine was not there, but at the final point, if you see, it is higher in the post-treatment. It was there. Total residual chlorine. We don't have an idea why it came inside, and still we are debugging with a chemical engineer to understand why this total residual chlorine came into picture. So the advantage of nanomaterials, yes, you have cost reduction. Yes, you have size reduction. Yes, you have very good efficiency. The uncertain areas are, than saying opportunities, I'll say uncertain areas are, certain reactions are not under our control. And certain residual patterns, why it is coming, still has to be explored. And the kind of additional elements that has been placed into the system is still need to be explored. And the kind of things, and when you go into the elemental level analysis, when you do EDX, I hope everyone are well aware about EDX. EDX, it will give you the kind of elements that are present. Almost it can give, any EDX can give up to 29 elements that are present. And if you want selective element, you can go for ICP OES to find what is the concentration, right? Once again, repeating the same. So that will give you an idea what are the elements that are additionally added and which need to be controlled. So if you ask me what arrangement you have done in this reactor to control the chlorine, or if you ask me what the element you have done for here, I'll say I don't have any idea. And if you ask me, because of this effect, oil and grease, without having any trap on oil and grease, I'll say like, yes, my system will work like this nanomaterial, what I have designed will take care of oil and grease. This is the post impact. This is not a pre-planned impact. So that is a complex nature of nanomaterial from my experience on treatment techniques. So exactly 45 minutes, I'm closing here. So say session is open, you can, if you have queries, yes, please.
Yeah. Any queries? You can drop in the chat box as well.
Hello, Professor Ram Sundaram, sir.
Yes, please.
Yeah, sir, you have given a very good idea about the degradation of textile dyes through developed some methods now. So in most of the cases of textile effluents, we'll be having a lot of salts, right? So how far these nanoparticles interacts with the different kinds of salt material which are present in the effluents, or what is your opinion on that? How to overcome these challenges with respect to conductivity or with respect to the particle nature?
So from our analysis, we just understood, this is basically my opinion across. We understood like, yes, there are a lot of salts which makes the process difficult in case of application of nanoparticles. And the first attempt of putting this nanomaterial without analyzing what are the salts present, we found like, yes, got absorbed in the nature. The moment you have negatively charged ions inside, when you post a positively charged ions get absorbed. That's a phenomena we just observed. And we found like if your charged particle is not capable, for example, you have a lot of positive charges inside and you have given a positive charge ion nanomaterial inside, then there is no proper reaction. So basically, you have to analyze what kind of salts are there and proper choice of nanomaterial will do it. And iron oxide, the choice we went for it is almost positively charged and it has 2 layers which can be gelled up to get a negative charge. Oxide will take off negative.
Okay, fine.
Yeah. If the forward osmosis, so how material should be clean when it is saturated? Yeah, that is the question I have just thrown across. That is what we are trying to see what to do on forward osmosis when you want to clean the chamber. The usual recommended method is backwash. When we do the backwash, we felt like the layers are getting separated, right? Because the velocity which has been forced across onto the membrane is higher. The moment I found the reason, I'll share with you. Ms. Pooja Tatola. I need to find it. Still, we are in research. We are not able to get it done. And in fact, tomorrow morning when I start, I'll go into the process of simulating your membrane, and I'll show how this is happening in terms of fluid dynamics. What is this happening? Any other queries you have? Good to know. Good to know. It is a quite challenging one.
I'm also working in BSc. Okay.
Sir, you said that we have to use nanoparticles according to the compounds we have to separate. Which type of nanoparticles are providing better results in biomolecule separation? And for biomolecule separation, I'll recommend you don't go for chemical-based nanomaterials. Now there are bio nanofibers that are being widely used across. And in fact, I have come across a month back, like they are trying with rice-based straws to do the biomolecule separations. When you go for chemical-based nanomaterials for biomolecule separation, the efficiency is not in a encouraging manner. And that is what my inference is all about. Just go for bio nanofibers. Actually, it is tough writing everything in chat box. Yes, you can, if you are allowed, you can unmute and ask question.
Yeah, Pooja, you can unmute yourself and then you can ask the questions.
Hello, good afternoon, sir. Pooja this side. Sir, actually, I am also working in biological activated carbon for wastewater treatment. When we do the, we are also developing a nanoparticle of carbon in the presence of nitrogen. So the problem came while I am working is when we do backwashing of the carbon. The packed column is disturbed a lot when we backwash that column. So is it any method that how can we clean the bed after the bed gets saturated?
That is nicely pointed out. The same problem exists everywhere, I think so. And one sort of solution which we are trying it, you can also try it. I don't know whether it will give you a proper result or not. We are trying to make sure, like when you do the binding of the particles, whether it is possible to have a resin in between. Okay. That is how this graphite has been formed. When they are doing this 1D to 2D graphite, they are using a resin format to hold the columns in pack. Right.
Okay.
But the success ratio of
it,
it's still I have to try. We are just synthesizing it.
And oil and grease is also a major problem, sir, when we are working with grey water treatment.
True.
In grey water, there is lot of oil and grease, so it also we are getting a problem while we are running the bed. So it also affecting the life of the bed. If the bed is once working for 7 days in 1 ml flow rate. When the grey water we pass through it, the life of the bed is come to 5 day. So the oil and grease is also problematic to the bed. So what is there is any method we are using coagulation or flocculation for to solve this problem, but still is this not working? So will you please give any suggestion, so how can we overcome this
So
problem?
just now I said to you, Ms. Pooja, like one is like oil and grease, we have not ever expected that it will get treated in our system, because we know it is going to create a huge drawback to the content of treatment. And then we thought of putting a separate oil and grease separator. But fortunately, this iron has a property of removing it. Why can't you try that? This is from the experience. Why can't
Okay,
you
sir.
try that when you have iron oxide into it? When you are specific about a single nanomaterial, is fine. If it is possible to make a composite, try it out, because from the experiments and from the results, we understood that iron oxide is capable of removing it. That is, which is not desired from our end, but it has been proved like it has been removing it. And now we have cut down this oil and grease separator, because already the nanometer is taking care of the same thing.
Okay, sir. Okay, thank you so much for your suggestions, sir.
Just
Thank
try
you.
to come up with a composite, and if I find this backwash concept working from our end, I'll communicate it.
Okay, sir. Okay, sir. I will mail you, drop mail for
Sure,
to you
sure,
also for
sure.
yeah. Thank you, sir.
Thank you. So there are no questions. Thank you all.
I
On to
think
Dr. Barnett.
if there are no questions, then we can close the session for today. Okay, so if still the participants can still go through about today's topic, and if there are any questions, you can we can discuss it tomorrow. That is point number one, and then tomorrow the session starts at 11 o'clock in the morning. The link will be circulated. Already the file has been circulated, the Word file, and then it will also be posted in WhatsApp. So thank you all for joining. So let us meet tomorrow. Thank you, Dr. Ram, as well as Professor Hadas, for the second session, that is in the later half of the today's session. Thank you for taking the lead. And then tomorrow, the first session will be from the Dr. Ram side, and then the second session, afternoon session, will be from Professor Hadas. Thank you.
Thank you all.
Thank you. Thank you all.
Thank you. Could I end the session? Shall I?
Sir, you can make me as a host. You can make me as a host. I need to do a couple of things. Then
1 minute, I'll make you as a host. Yes.
Yeah.
I've done it.